So welcome everyone. Thanks for coming, and thanks to Lucy for coming virtually to talk at the Bristol Centre for Science and Philosophy of Science series talks. Lucy is a University of Bristol alumni. She did a joint philosophy and physics degree and master's here, and she's now at King's College London doing a PhD in philosophy of physics under the supervision of Eleanor Knox and Alexander Franklin. Today she's going to be giving a talk titled Records, Retrodiction and Macroscopic Asymmetry. So I will hand it over to Lucy.
Great, hi, let me just get the screen up. There we go. So yes, thank you for having me here. Really excited to be able to present this. I'm very excited to hear all your thoughts. So hopefully I'll have lots of questions. So what I'm presenting today is a chapter of my thesis, which is overall looking at the difference between the past and the future and linking that to the metaphysics. So what I'm aiming to do in this presentation is lay out one of the main theories of records, and which is the basis of the information asymmetry within time, which is a huge difference between what we know about the past and what we know about the future. It comes out in the form of records. We have all these photos and memories and all these systems which seem to tell us about the past in a way that we don't have of the future. So I'm going to aim to present David Albert's view of records and why I think it goes wrong. I think there's some problems with it, and then try and present my own view, which is sort of a rough suggestion, sort of not fully fleshed out yet, but just sort of to describe how I think we should characterize records. And then I'm going to argue that based on this characterization, we should see that records are macroscopic, and I'm using macroscopic quite loosely in this sense, but I'll get to that later. So that's the kind of plan of the talk. So just let me make sure the slides are working. There we go. Yeah. So that's what I basically just said. I'll start by looking at the difference between what a record is and what retrodiction is. These are the two ways that we can get information about the past. I'll then go into Albert's accounts and the challenges to it, offer my alternative counts, look at why records can't be microscopic, and then I'll look at two possible counterexamples to that claim and show why they fail, which will help explain why records can't be microscopic. So it's quite a lot to get through, so hopefully I won't have to rush at the end, but I think hopefully I've planned it right. So let me just sorting out the slides. They're coming off a bit funny on my screen. There we go, that's better. Yes, so starting off with, I'm looking at the difference between records and retrodiction. So retrodiction is simply when you take the present state of the universe and you evolve it backwards using the law of physics to find out a past state, find out information about the past. So this is basically there's just the reverse of prediction. It's an entirely symmetric process. We can do this towards the past and towards the future. And within physics, at least, this is the main way that we use the laws of nature. We evolve states forwards and backwards to find out what happens, what the evolution, or how the evolution occurs. Records, however, are a distinct way to find out about the past, or at least they seem to be. They are systems which give very detailed and far-reaching information about a very specific part of the past. And they seem to give this information in a very direct way. We look at a photograph and we instantly find out about the content of the photograph without having to do any of the calculations that are needed in retrodiction. So an easy example is if we're trying to find out about what the night sky looked like 2 weeks ago, to do a full retrodiction, to find out via retrodiction, we have to do a full calculation of all the positions of the stars and the planets in the sky and work out, using the revolution of the Earth, all of these laws to calculate exactly where every item in the sky would have been to find out that information. But if we have a photograph of the night sky 2 weeks ago, we can find all that out instantly without any calculation, without having to do any work about taking into account the position of the Earth, where you are on the Earth, all of that kind of thing. We just look at a photo and it gives us that information directly. Though we don't find anything beyond that information. When we do a retrodiction, we'll find out a whole lot of extra information. A record is much more limited. It will give information just about the thing it's recording, and in a very direct and detailed way. So that's the kind of an easy characterization of the difference between them. And the puzzle that we have is that we seem to have all these records of the past and not of the future. And that explains, a huge amount of the difference between why we view the past and the future differently. So in this talk, I'm not going to try and answer the question absolutely of why there's an asymmetry there. I'm going to try and characterize records in a way that hints towards that answer and tries to connect it to the literature on thermodynamic asymmetry. And that is the common way that in the literature people are trying to explain this phenomenon by linking it to thermodynamics. And Albert's view, which I'll present in a second, is very much focused on this asymmetry. And I think that is where his account falls down, is that he's so focused on the asymmetry question that some of the details of how we use records and what records really are get lost in, and that makes his account unsatisfactory. So I'm going to start with accounting for what records are and characterizing them, looking at the practical ways we use them. And then hopefully that will hint towards arguments for an asymmetry argument, which can be fully developed later on. So looking at Albert's account of records. So for Albert, records and retrodiction are two very distinctly different processes. He separates them out into retrodiction, which is the process I've described, and then records, which he describes as a kind of measurement. So he compares them to all of the measuring devices we use, as well as just a more general process that is what we use to set up measuring devices. So that process uses something called a ready state. So I've got a diagram here just to show what I mean. So you start with a ready state, which is a state in the past, and we know that's what that state is. And from that state, we can calculate the expected evolution of the system, just using the normal laws of prediction or something like that, to get to what we expect to see in the present. And then we look at the actual present state, and if we notice a difference between the actual state and what we expect based on the ready state, we can infer that at some point in the intervening interval, there must have been an interaction which caused those changes in the present state. And so the actual present state acts as a record of that interaction. And that's what he defines as a record. He defines it by way of this mechanism using ready states. And his argument is all about the fact that if you have these two states that the present state and this ready state in the past, you can find out information about the intervening interval. And what's interesting is that unlike retrodiction, with retrodiction, you take the present state and you evolve and you find out about the past state of that system itself. Records are distinct from that in that where this process tells us about an interaction with a second system, which we haven't involved so far. We don't know what the system is. We might be able to infer what it is, but all of the information we have is about one system and tells us about a second system which has interacted with it. So that's one of the big distinctions between records and retrodiction. So that's just a nice statement of what I just said. The difference between the expected ready state and actual present state is what gives us information about the interaction. So his idea of the ready state is really key to this. He basically says, and this is also the source of his asymmetry argument, is the idea of this ready state, because he argues that we need to use this ready state, otherwise we don't have this start and end of the interval to be able to make inferences about what happened in between. So we need to have a separate record of this ready state so that we can do this inference about the record we have. However, to use this record of the ready state, that in itself is a record, and it needs its own ready state for us to be able to get any information from it, because records you would get information because of the ready state. So you've now got a third ready state, and therefore you need a third record for this to record this ready state. And he argues this leads to an infinite regress in your ready states. And you just keep going back. Every record you have, you need a ready state, and you need a record of a ready state, so on and so on, all the way back to the beginning of time. And he argues that there is a way we can stop this infinite regress in the past, in the form of the past hypothesis, which is essentially, he calls it the mother of all ready conditions. It's a state that we can have in the past, which we're sure happened in the past, and we're not sure because we need a record of it. We're sure because we've hypothesized that it must be there to explain the universe we have. We've just put it in there as an assumption without any need for justification. I mean, our justification is the world we see around us and that it's necessary to make that work. So that's, in that way, we can link all of our records, infinite regress going back, and we get to the beginning of the universe with the Big Bang. We have the past hypothesis, and that's our final ready state, and all of the measurements in between come from that. But there's no corresponding future hypothesis to stop the regress going forwards. And since you get an asymmetry between the past and the future, where you can stop the regress and you can base the reliability of all your records on this regress back to the past hypothesis, but going forwards, you can't stop that regress. And so your records aren't informative because you can't establish a ready state that's reliable in the future. So another way to think about this argument is in terms of phase spaces, in terms of thermodynamics language. If you take just the present state in a phase space, you can take just one point in phase space. You can go from that point to anywhere in the rest of phase space, bound by dynamical laws. So in the future and in the past, you can take infinitely many different paths through a phase space, infinitely many different possible histories and futures. However, if you add in the past hypothesis, you're adding in a second state in phase space, which the evolution has to start in. So it now has to start in the past hypothesis and go through the current present state, which drastically limits the number of options that the paths can go through, because they have to go through both of these states now. So you've really reduced your possible set of histories that you're going to be considering when you're looking at the history of the universe. But you haven't reduced the set of possible futures. So you've now got a much reduced set of histories and a big open set of futures, which corresponds, he claims, to an asymmetry in information about the past and the future. And overall, as an argument of asymmetry, there does seem to be a difference there, which he's identified, and there is a good basis for that. However, I think it has four main challenges to this view, both to his view of asymmetry and to his view of what counts as a record. And I think the asymmetry question comes down to this lack of specificity in what he's counting as a record. So the first question you want to ask is, you've got this big overall asymmetry that he's established between the past and the future, which is based on the past hypothesis. But that's a very long way in the past. We want to look at how this translates to asymmetry on a local level. And Albert argues that a sense of this process of using a ready state, linking it back to another ready state and another until you get this infinite regress back to the past hypothesis. He says this is hardwired into the cognitive apparatus of any well-adapted biological species, which is a very vague statement. It's just part of our nature that we're aware that we can trust records of the past, but we can't trust records of the future. And so even if we don't explicitly calculate this link back to the past hypothesis, we're aware that it exists, and therefore our minds are built around this fact, and our whole nature is geared from past to future to reflect this. This leads to a second question, does this actually match what we use records for? And this sort of foggy sense he's talking about is where I think we're losing a lot of clarity in his picture of what it actually means to use a record. Because I would say that when you're looking at an explicit measurement device, it does seem to match the picture he's talking about in terms of we have a definite starting point, which is our ready state. We then interact as something changes, and we get a change in the final state, and we can infer something about the interaction in between. However, if we actually look at most records we use in our day-to-day lives, we never really think about anything like a ready state. When we're using just our memories in our brain, we're definitely not using ready state. Even when we look at a photograph, presumably the ready state for that would be in the case of film photography, the undeveloped film before it's interacted with light. But again, this is not something we ever think about. We don't need a record of the film, the film with the photograph to be able to understand the photograph. We just look at the photograph and we know what it is. So Albert's account is quite idealized. It's based very much on the physical process of measurement and that's a very formal process within physics, and not much on the actual records we seem to use. So there's still something to explain in terms of how we get from this general process to a practical use of records. And the next question is also related to this, in that we don't seem to use these ready states, and we seem to get records directly. And also he's argued that the difference in asymmetry is because there's an infinite regress in both directions towards the past and the future. Theoretically, we could know a ready state in the future. and use it to infer an interaction between that future point and now, which is also in the future. And he argues that simply we cannot end this infinite regress towards the future, and therefore we can't trust these records of the future. However, we don't have anything like a regress towards the future that I can see. When we have memories of the past, we don't have memories of the future that we just don't trust. We just don't have memories. And the same with photographs and fossils and all of these systems which tell us about the past and our records. There's nothing like that which corresponds to the start of something we could know about the future. So it seems to be that if we're relying on just ending the infinite regress in one direction but not the other, we've missed an explanation of why these systems are existing on a local level and how they're directed at a local level, because we don't have this picture of an infinite regress in both directions at the local level. And this leads us on to the fourth objection, which is a little different from the others, coming from a slightly different angle. And this is that Albert's method only works for very idealized system. You have to have a ready state, a single interaction in between leading to the present state. If you have more than one interaction, or simply a very complex interaction, the changes between the ready state and the record, the present state, no longer allow us to infer anything, because if they're too confused, too convoluted, we may not be able to identify anything about the interaction except that an interaction has happened. So it may still act as a record in that we know something's happened to it, but we don't really get any information out of that. It only works when you've got a very basic system. So the example that Albert uses to clarify this a bit is he uses the idea of a billiard ball, which is sitting on a table. So the present state is that we have a billiard ball at rest on a table. And the record we have is that we have a memory of it 5 seconds ago where the ball was moving. And we don't know what's happened in between those 5 seconds, but we know it was moving, we know it's now at rest. So we can infer that at some point there was a collision and the billiard ball was stopped. But we don't know anything more than that. That's a very sort of basic record. And it's certainly we can infer something, but we don't know if it's stopped because of a collision with another billiard ball, or because someone's reached in and stopped it, or because any of these multiple possible reasons why that change could have occurred. And it also seems slightly an odd definition of records, in that he said that a billiard ball sitting at rest on a table is a record. In most cases, we wouldn't consider that a record. It's only a record because we know the ready state. Most records, we don't need to have that extra information to make it a record. A photograph doesn't need extra information. It just is a record in itself, and we can see that immediately by looking at it. So that's another way in which this characterization of records is very idealized, it's very abstract, and doesn't really reflect what we use on a practical day-to-day basis when we're identifying records. So I'm now going to present an alternative account to Albert's. And I'm presenting it as a kind of, not a rebuttal of Albert, but a kind of a different conception. I actually think my view and Albert's view end up being compatible overall, because mine is focused on this question of the practical local asymmetry, which we see every day, while Albert's is, as we've said, focused on this overarching asymmetry. So I think someone who likes Albert's views, and I do think there's a lot worth looking at within Albert's ideas, it's perfectly compatible with the view that I'm going to present. And also, because I'm not trying to answer the asymmetry question, it's perfectly possible that Albert's explanation of asymmetry in some way could be built into the picture I'm going to present as well. But I'll give a bit more detail on that kind of thing later. So to start with, I want to go back to the distinction between records and retrodiction that Albert draws very strongly. He argues that these are fundamentally different methods that we have of learning about the past. And I want to say that they're not nearly as different as we think they are. And there's actually a lot of similarity between the techniques we're using in both cases. And in reality, they're all on the same scale. And we see them as two distinct differences because we're on two ends of the scale, but there's a whole spectrum in between, which is a kind of something which is like a record, but you're also using retrodiction. And I think that will clarify what's really going on when we're using records. So full retrodiction requires taking the fully specified present state of the universe and performing a rigorous calculation on it. And to do this without errors, you need deterministic laws for one thing, which we'll put that question aside for now, but you also need all of the microscopic details of the universe. You might be limited by relativity and how large a section of the universe you need and how far in the past you're planning to retrodict, but you need a relatively large section of the universe specified in full detail. And along with things like the state of the space-time, things like that, all of these things need to be specified so you can do this full retrodiction. But in practice, that's completely impractical and we never do that. Instead, we take a lot of shortcuts based on higher level laws, or within the laws of physics as well. Things like the laws of thermodynamics are macroscopic laws, and we're looking at concepts like entropy and things like that. They're defined on a macroscopic level, but also a lot of other laws just governing macroscopic bodies and forces and all of these things we can use, which allow us to ignore a lot of details about the systems we're retrodicting with. And we also often treat systems as isolated when in reality they're not. And all of these shortcuts allow us to make retrodiction a reasonable process that we can actually compute and get information from. So the key to this happening is that we have stable systems in the universe that we can treat as isolated, and we can treat as obeying these laws and ignoring these microscopic details or any sort of wider details. So another way to sort of more formally describe this process is what David Wallace introduces which he calls historical inference, which is basically the idea of you use all this extra information you have about the world to guess a past state, and that's exactly what we do when we're looking at things like the past hypothesis. We take the universe we have and we say that looking at the general features of the world, it must have been roughly this in the past to lead to where we are today. And we can check that using a rigorous calculation, but often we don't bother doing that. Or they might do it the first time someone does it, but after that, you get used to the guesses you're making and you just sort of make an inference. And a lot of this uses things like cause and effect. In the less sort of physicsy field, you can infer from the ideas of cause and effect what's happened in the past. So for example, if you're looking at a tree and you're looking at brown leaves that have fallen under the tree, we can just infer that in the past those leaves were green and on the tree. That's just using a basic knowledge of cause and effect, the passing of the seasons, the effect that has on the leaves. And all of that knowledge allows us to ignore a full calculation. We don't need to calculate that using biology or physics. We can just infer that very directly. So historical inference is a sort of a rigorous way to describe that process, though it is, again, that's quite a physicsy terms. The historical inference is this rigorous calculation to check your guess. In most cases, we just stop at the guess. So once you're looking at that sort of retrodiction, the difference between records and retrodiction becomes a lot less pronounced. The information you're getting using the shortcuts is very direct in the way that records give us information. So the example I just used was leaves under a tree. So when we look at leaves under a tree, we instantly can infer that they were once green and on the tree. We don't have to do any work to do that, in the same way that when we look at a photograph, we instantly get information about its contents. So that already closes a lot of the gap between records and retrodiction. So what I want to propose is that these are basically two ends of the same scale. And with retrodiction, the evolution between the past state and the present state has to be worked out in full to get information. You have to work out every step of that evolution. But as we move towards the records end, we can skip a lot of that evolution because we either can make a wide statement about what it's likely to have, that evolution is likely to have been, or in the case of records fully, that evolution just doesn't matter. It doesn't matter how a photograph has changed between the moment of the photograph being taken and now it's still a record. That evolution doesn't matter. So these are both the same process. They're both the same process using the laws that we have. It's just that there's a lot of laws that we can use which make these processes a lot easier. So based on this idea, I want to explain a bit more fully what I'm going to characterize records as. So when a system is informative in the way that a record is, it means that the state of the system is correlated to another system, such that the state of that system tells us something about the other system. So a record tells us about the past because changes to that past system will change the record. If I take a photograph, if I change the scene that I'm photographing, it will change the photograph I end up with. And that correlation is why I can use the photograph to tell me about the contents of the photograph, because I know there's a correlation there. I can identify that correlation, and therefore I know that this photograph represents something. So this correlation needs to be there, and we also need to be able to identify this correlation. So this isn't anything to do really with what the record is or what system it is. There's many different possible systems that can be records. You know, a photograph could be very different from a human memory. Those are very different systems, but they're all backed in the same way. And at the same time, if you take the difference between a photograph and a painting, those are two systems that are very similar, but are very different, because a photograph is informative. It tells us about the thing it's photographed, while a painting doesn't tell us anything really about the picture that it's depicting, because we don't have a correlation between a painting and the subject of the painting, because there may be artistic liberties taken. It could be completely from the imagination. It's not necessarily telling. It may be an accurate painting of a landscape, but there's no way to identify that correlation in the way that there is with a picture. So a system has to have this correlation, and we have to identify this correlation. So to have this correlation and to be able to identify it, I want to say that the correlation is robust. And what I mean by that is that it won't be disrupted by other interactions. It will be a robust correlation between these two systems, the record and the system being recorded. And other systems interacting with the record won't destroy that correlation. They won't significantly alter the record in a way that means it's no longer informative. Because if other interactions take place and the record has changed, then we can no longer say that changes to the record correspond to changes to the system being recorded. And that means it's no longer informative. So this correlation needs to be robust against these kind of changes. And we can characterize these other interactions by calling them noise. It's a term that's very familiar from communication theory and information theory. So defining noise as any unwanted modifications to the record, which aren't a result of the system being recorded. So those can be very small changes, and they often are very small changes to the record, or they can be big changes which destroy the record completely by destroying that correlation. But a correlation between a record and the system should be robust against most sources of noise, in the same way that a signal is when we pass it through a digital signal through a device. We expect that there may be some interactions, sources of noise from outside the system, from electromagnetic fields, from the equipment, which may introduce errors into a signal. But overall, the correlation between the final signal and the initial output of the signal is robust against these changes. So that's what I want to define a record as, a system with this robust correlation to the past system. So this so far is not all that different from Albert's account. It's just basically a way of describing what you need to occur in the interaction between the ready state and the initial and the final state. So my force objection against Albert was that he doesn't have a way of dealing with complex systems where complex interactions happen or multiple interactions happen. This account, in terms of robust correlations, would deal with that, because it's requiring that other interactions don't significantly alter this correlation between the interaction and the final record. And it allows for much more complicated systems where multiple interactions are happening, or the interaction may be complicated. So long as the interaction produces a consistent change to the record, and that's not destroyed by other interactions, we have a record. But we're still left with the question of, how do we get sort of information about this, from this record, and how do we identify a correlation? So, and this is a key part of a record, is that we have to be able to see that there is one correlation which stands out over and above any other correlation to any other systems. So a photograph is correlated simply to the scenery it's a picture of. It's not correlated to any other systems. There's just one correlation that stands out to us, and that's what allows us to identify the record. And the method that Albert describes is one way to identify a correlation. If we have a ready state and we have a current state that's different from what we'd expect based on the ready state, then we can identify a correlation between the changes in the present state from what we expect it to be, and we can identify a correlation between that and an interaction that must have occurred. So that allows us to pull out the information we need in one way. But this isn't the only way to identify a correlation, precisely because of the reasons I've discussed when looking at records and retrodiction. Because these two methods aren't dissimilar, a lot of retrodiction relies on stable systems where the evolution of a system is very easy to predict. And the key part of Albert's method is not, in fact, the ready state. It's the expected evolution and the difference between the expected evolution and the actual current state. That's what allows us to identify that something has occurred, and allows us to get information about this thing that's occurred. But using most methods of retrodiction, we can very easily identify how we expect a system to have evolved in the past without doing a full retrodiction, without the need of a ready state. And we can use this to identify a record exactly in the same way that Albert's method is described. We look at what we expect to be an evolution of a system. We identify that the actual state doesn't match that, and we infer that something must have happened. So an easy example of this is a broken branch. We know that given all the laws of nature and biology, a branch will grow in a whole straight line. It will be united, it won't be broken in any way. So if we see a broken branch, we can infer that something must have impacted that branch to have broken it. And it's a very basic record. We're not getting a lot of information from it, but we are getting some. And so it's acting as a record. We didn't need any specific ready state to do that. We're just using essentially a very basic process of retrodiction using the laws of biology and our knowledge of branches and branch-like systems in the world. So to identify what we expect that system to behave like, and therefore we can identify when it deviates from that. Okay, so yes, that's just another statement, just restating that. So we've already seen this. Based on stable systems in the universe, we can identify this past evolution. Okay, so I hope that's fairly clear. I want to move on now to why this argument means that records have to be macroscopic. And I'm hoping that a large part of the point I'm about to make has already become clear in the way that I'm talking about stability and high-level laws. But I'm going to go through it explicitly as well, and then look at two possible counterexamples, which I think explain in a lot more detail what I'm really talking about when I'm with this description of records. So the overall reasons why records must be macroscopic are this need for stability and robustness for us to be able to get information out. And just to clarify here, when I'm saying macroscopic, I'm using a very loose sense of the term. The difference between macroscopic and microscopic is quite vague anyway, and I'm definitely pushing it a little bit here. What I basically mean is that as you get smaller and smaller, there comes a point where you can no longer reliably have records. That point may be very, very small, and what we would ordinarily count as microscopic. So I'm just calling it macroscopic as a way to label two sizes. But the point remains that at the very smallest level, you can't have a reliable record because it won't be robust and we won't be able to identify a stable evolution. So to justify this a little bit, Adam Elgar in his 2005 paper gives some arguments to explain why folk physics, such as laws of cause and effect and the kind of everyday processes we see, why those processes are so reliable when they have so little basis on physics, why we're able to have such effective high-level descriptions of the world that we use on a day-to-day basis without using any physics. And he gives three main arguments for this. His first is that forces affecting objects generally typically are very short range. So you have the strong and weak nuclear forces, electromagnetic forces. These are typically short range, and they're quite rare to interact with, even in the case of electromagnetic fields, which are slightly longer range. There's not a lot of objects that have strong electromagnetic fields and not a lot of objects that react to them. So we can mainly ignore those forces. The only exception is gravitational forces, which does have a long range. But the second point is that over large distances, gravitational forces are very weak, and they only typically affect very small changes in systems. So we may say that the sort of classic examples of things like a supernova in the Andromeda galaxy might affect the position of this particle on Earth. But that's a very weak effect. It's a very small effect. And within the area of Earth, there are no large fluctuations of mass distribution which would cause significant gravitational effects. Beyond that of the Earth itself, a very stable and predictable gravitational effect. And his third reason is a more general reason of why macroscopic systems are so generally useful. And he argues that statistical mechanics is a very good tool for describing the behavior of large complex systems in a way that allows us to ignore all of the microscopic details. I mean, there's lots of arguments about emergence in statistical mechanics, which are sort of putting aside to one side for now. But the overall point is that we can describe very large complex macroscopic systems with very stable behavior, which doesn't concern the exact microscopic details, which helps to shield out things like the effects of a distant supernova, which has a microscopic effect on the position of particles on Earth. Under statistical mechanics, it means that small changes to microscopic conditions like that are unlikely to affect the overall behavior of an object. So these three reasons, Algor argues, is what allows us to perform such easy descriptions of a macroscopic world without having to worry about the detailed laws of microscopic physics. We have a very stable macroscopic world. So based on this, linking it back to the arguments I've made for records, we can see that if records rely on stable systems, which are precisely those that are robust against lots of different kinds of interactions, they're robust against small sources of noise, such as internal fluctuations of the system, small changes to the microscopic configuration, you're going to need a macroscopic system to be able to achieve that level of robustness. And we see that all around us, in that a system is very predictable. So to clarify this a lot further, I want to look at, first of all, the example of a one-molecule memory device. So this is a system which we might think immediately is a microscopic memory device and forms a microscopic record. But I'm going to show that it's not, for exactly the reasons I've described, and that the system isn't stable and it's prone to being disrupted by noise. So this example comes from the literature on Landau's principle, looking at the thermodynamic costs of measurement and erasure of systems. I'm not going to explain the literature on Landau's principle. I just want to pick out this one example and crucially use an objection to this from Norton, his 2011 paper, though he's and other papers as well. So how this example works is that you have a box with a partition in it and a single molecule of gas floating around in that box. And by inserting the partition, you can separate the box into two states, one with the molecule trapped on the left and one with the molecule trapped on the right. And this represents a simple bit, a 0 and a 1 value bit, with the two sides of the partition. And in the literature on Landau's principle, this is used as an example of a way to measure a system. You measure which side of the box particle is in, and then an identical system is used as a memory device, and which side of the box you trap the particle in corresponds to the information about which side of the box the particle is in, a very simple system. And the removal and insertion of the partition has a thermodynamic cost, which is associated with Landau's principle. But again, leaving aside those full thermodynamic processes, the objection that Norton has to this system is that thermal fluctuations will destroy any stability the system has in a way that makes the record unreadable. He also has a sort of a larger argument about the fluctuations' effect on thermodynamic processes and Landau's principle generally, but I just want to take what he says about fluctuations and stability of the system without addressing his claims more generally. So an example he uses to explain this is describing how we take a measurement of which side of the box this particle is in. So he describes a process where you lower a sort of keel-shaped device into the top of this this box, and it goes in where the partition is. And based on which side the molecule is, the molecule will bounce off one side of that keel, and the force of the molecule will cause the keel to tip and reveal which side the molecule is in. And Norton argues that for the keel to be light enough to be affected by the molecule, it has to have a certain thermal energy, which is very similar to the molecule itself. And this means that it will be very, very easy to tip. And the thermal energy of the molecule itself will fluctuate, because that's what any thermal system will do. It will have fluctuations in its energy levels. And this fluctuation will be enough to tip the keel, and it will give us a false reading of which side the molecule is in. So this is just one process. This is just one description of one way you could measure the molecule's position. There are lots of other things, but he says this argument will apply to whatever you try and do to the system. For things to be small enough and sensitive enough at this level, they have to have these available thermal energy, and this thermal energy will fluctuate back and forth in a way that destroys whatever process you're trying to achieve. That's Norton's argument. So as a response to this, Myrvold has tried to prove Landau's principle in a way that accounts for fluctuations. So again, I'm not going to look at his full argument. I'm just going to look at how it relates to this one molecule gas device. What he does is first of all, he uses potential wells instead of a physical box to run a physical partition to control the position of the particle. So this removes a lot of problems in terms of the manipulation of the partition and all those kind of things. And the second thing he does is that he uses all his calculations using the expectation values of variables rather than the exact position. And what this allows him to do is prove Landau's principle on a statistical level using expectation values, which is exactly what matches in the physics literature. When you see Landau's principle in the physics literature, it's taken to held statistically. And in terms of the one molecule gas memory device, what this means is that a single use of the memory device could be affected by fluctuations, but it isn't necessarily. The fluctuations may not affect it, especially as there's been points from Ladyman and Robertson as an objection to Norton, arguing that fluctuations, although they will fluctuate over the full energy range of the system, these fluctuations they're in a Gaussian curve over the expectation values. So they'll be centered around the middle. They'll normally be very small fluctuations, and only rarely will you get these extreme fluctuations, which would destroy the process you're trying to do. So Myrvold's results show that taking into account these fluctuations, you can still have a memory device on a microscopic level that holds statistically. However, the statistical nature of his analysis essentially means that only over a long sequence of trials will it perform as expected. And when you're translating this into a single microscopic measuring device, you can't rely on that measuring device because it could be affected, it could not be. And you can't know the difference unless you do a long sequence of trials to see if it agrees with that long sequence. And if you're transforming that long sequence of trials into an instantaneous measurement, then you're going to need a macroscopic symbol of many identical copies of the system all performing the same task. And the overall majority result of the ensemble will be the reliable record. However, each individual microscopic system is not a record. Only when you take it alongside this long sequence of trials or alongside this macroscopic ensemble do you have a memory device that you can actually use. So the second example I want to look at is essentially a practical example of exactly this process. So it's used in quantum computing, which is another example of something which is clearly a microscopic process, and clearly we're having a lot of success with quantum computing. So what they actually do in quantum computing is, first of all, they try and protect as much as they can against noise in systems, and they can do that to a very large degree, but they can't eliminate it completely. There's inherent sources of internal fluctuations, such as the thermal fluctuations I've described in Norton's case, and also due to quantum effects, there's just internal sources of noise that can't be eliminated. And Shaw's paper in 1995 developed a quantum error correcting code where a single qubit is replaced by a set of entangled qubits. So Shaw's original proof uses 9 qubits. So I think the current work has shown that you can take it down to just 5 qubits. And what this means is you have a set of entangled qubits which represent the state rather than a single one. And when you're accounting for noise, it is unlikely that all of your set is going to be affected by noise. So you can see on the screen, I've just got a diagram of what that means. So I've done it in terms of 3 qubits, just for simplicity. So if you take a 0, 0, 0 state and it's run through a system and it's affected by noise, it might flip the state of one of the qubits. So you now have a 0, 0, 1 state. However, you can then perform a simple algorithm which will take it back to the initial 0, 0, 0 state. And the same for 1, 1, 1 states. So this essentially is exactly what Myrvold's described. You can't rely on a single qubit not to be affected by noise, but if you take a set all behaving exactly the same way, making the exact same measurement, recording the same information, then you can be sure that over the set, only 1 or 2 will be affected by noise and the overall result will hold. But you've immediately moved away from your microscopic argument. And I mean, it's very easy to say that 5 qubits is still microscopic, and I don't deny that we're getting very small here, but there does come a cutoff point where you can't go below 5 qubits. You can't use just 1 because it will be affected to noise. And obviously quantum computing is a very idealized system. It's one that's specifically designed to be very accurate in exactly the way we want it to be, and in a way that protects against noise and all of these fluctuations and other influences. Most records, more generally, things like a photograph, are just natural systems, and they're much less designed, they're much less specialized. So the effects of noise are going to be a lot less, they're going to be a lot less protected against that. And generally in more complex systems, this will be a lot more relevant. So you can get very small in very specialized circumstances, but even in these circumstances, there comes a cutoff point where you can't get any smaller and you no longer have microscopic memory devices. Okay, so that's everything I wanted to say. So just quickly going over that. So I started by saying that Albert's account of records fails to explain local asymmetry in the practical use of records. And then I've argued that records and retrodiction aren't fundamentally any different from each other. They exist on exactly the same scale based on how directly you can make an influence about the past. I then suggested that records are systems with robust correlations to the past state of some other system, and we can characterize this robustness in terms of robustness against noise. And these robust correlations are identifiable in systems that are stable and that we can easily predict the expected evolution of. And finally, I've argued that records can't exist on a microscopic scale. Okay, so that's just the references I've mentioned. Thank you for listening, and any questions?
Cool, thank you so much, Lucy. If we can give the speaker a round of applause. What we'll do is take a quick break and rejoin at 5 to 6, if that's okay with you, Lucy?
Mm-hmm.
Yeah, cool. So yeah, 4-minute break from now to get a cup of tea or get a glass of water, whatever, and then regroup at